All right. So I'm gonna get started here. Already like 4 minutes behind schedule. Alrighty. So does anyone have any questions about all the topics up to this point? Yes.
When we are adding 4-bit numbers,
Uh-huh.
not jump to 8-bit for the result.
Say that one more time.
Okay, we have two 4-bit numbers.
Yes.
Right? And the result eventually can be 8-bit numbers, or we have one extra.
If you're adding two 4-bit numbers, then your result can have up to 5 bits, not 8. If you're multiplying, it can be up to 8.
So basically, when we add into 4-bit number, we have to get a 4-bit answer.
That is correct. But you can have an extra carry bit to indicate that the entire addition results in a carry.
But consider this one extra carry.
Correct.
We have to jump to 5-bit number. Can we do this?
So when we talk about an n-bit adder, that means the input x and y and the sum, they all have to have the same number of bits. But you do have one extra carry bit. So in the case of a 4-bit adder, the extra carry bit is going to be the same as K4, because K0 is usually 0, assumed 0. So K1, K2, and K3 are used in the calculation of the sum, but K4 is kind of like hanging around, and that's your final or the output carry bit from a 4-bit adder. So is that okay?
I'm just looking forward if we can use it or not for further calculation.
You mean the carry bit?
Yes.
Yes. So we'll use the carry bit for certain things. For comparison, for sure, the carry bit or the borrow bit is very important. But for addition, the carry bit is what allows you to perform a wider addition than your processor can do. So if you have a, let's say, 8-bit processor, you can only add 2 8-bit numbers, in a single addition. So what do you do when you have 32-bit numbers to add? Well, the carry bit is going to be useful because you can, quote unquote, propagate that carry bit, to the other 8-bit numbers as you work it through from least significant to most significant. So we'll get to that most likely in the second half of the semester. After we get into like assembly language programming, then we can actually write subroutines to perform like multi-byte additions when our processor is only a byte-wide type of processor. So that's a good question, but we'll get to that part when we get to it. We'll revisit the use of the carry bit. Yes.
So when I was making the 3-bit adder, the carry look ahead. So for each carry, I needed respectively use carry for the first slot was 1 and, carry for the second was 2 ands, carry for the third was 3 and.
Yes.
So does it for a 32-bit adder, does it just increase the amount of ands
Yep.
So that's it. Okay, I was just wondering if there was more
And then for the final OR gate, the fan-in ratio of the OR gate is also increased accordingly.
Okay.
Yep. That's right. All right, so let me just kind of point to you what our lab for tonight is going to be. So the lab for tonight is down here, and it is, where did I put it? Right here. It's 3x3 carry look ahead adder, part 1. So there are several parts to it. For the most part, once you understand how to use a multi-bit gate and understand what is a carry look ahead adder, you should be able to do this, okay? But before you even try, okay, make sure that you can answer these questions. You have to know what is X, Y, Q, K, S, okay? If you're not familiar with those, symbols, it is time to kind of study the class notes and make sure you understand that first, because this particular lab refers to those letters in a confusing way, intentionally. Okay, so you got your warnings. Okay, but if you already know what those bits are, then you can get started pretty much right away. All right. Any other questions? So those were all good questions. So for one, we'll get to it in the second half of the class. And then for your question, did I answer your question? Yeah. Okay, good. Any other questions? No other questions? We all good? All right. So if there are no questions, our lab is actually a little bit behind the lecture, which is unusual for this class. But I'm okay with that. So what we'll do is we're going to talk about comparison of numbers, or comparison of the value represented by numbers. What is the difference? What is the difference of comparing binary numbers as opposed to comparing the values represented by binary numbers? Remember that number wheel thing that we talked about last time, the signed number representation thing? The same bit pattern can represent different values. So if you're talking about signed representation, then it has a different way of comparing as opposed to unsigned values. So signed versus unsigned, the way we compare is both the same and also different. Okay, I know that's awfully confusing, so that's kind of the objective of today's class, to clarify that. So the first thing we want to do is to say, well, how many comparison operators do we actually need? Okay, because there are like 6 of them, right? Less than or equal to, greater than or equal to, and then not equal to. Those are the 6 that we were introduced in C, C++, and basically throughout your life. What if I tell you we only need 1? And then some of you are thinking, no, not that NAND 2 gate thing again, right? Yes, it is kind of like that. All right, so this table should be fairly easy to read, okay? X is less than y if and only if x is less than y. I mean, that's it, okay? Because I want to boil everything down to just less than, okay? Forget about all the other comparison operators. I just want less than. But I will let you guys use logical operators, okay? So you can use and or not to help you, but I want to boil everything down to just less than. Second line, x is greater than y. I don't want greater than, I just want less than. But this one is easy. I can transpose the operands that is being compared, and it becomes less than again. Okay, so that's an easy one. X is less than or equal to y. Well, it boils down to it is not the case that y is less than x. Can you buy that? Okay. The other one, yeah, we can just transpose the position, and we're done with that. Yes?
What about being equal?
Huh?
What about being equal?
Well, you're looking ahead of me. So the next one is not equal to. Not equal to, as it turns out, is easier to express than equal to, because if x is less than y or y is less than x, hey, then they're different. Is that okay? And this is also why in some programming languages, not equal to is represented by less than greater than. Okay, if you look into, I think SQL is like that, and a few other programming languages also express not equal to with just less than greater than, because that's basically what it is. So now we get to x equal to y. Well, x equal to y means it is not the case that x is different from y, but because we already know how to express x is different from y, we just put a big negation on top of that. That's my lazy way of expressing it. Is that okay? Are we good so far? Okay. So yes, so that means all the other 5 comparison operators are not really needed. They could have taught C and C++ with just less than. And NAND, by the way. So NAND for logical operation, and then less than for comparison operation. You don't need any other stinking operators for Boolean expressions. But don't try to do that with your CISP 430 or 400 classes. Your professor may be a little bit upset about your program. But the bottom line is, a lot of things that we use by hand really is extra. They're not really needed, okay? It's just, it's handy to have those, but they're not really needed. So are we good so far with section 2? Where, I just say, but it is important, okay? This conclusion that we only need less than is important because I only have to show you in terms of logic gates how we find out whether a value is less than another value. The rest can be done just by using logical operators. Is that okay? Okay. So now we are going to move on to unsigned comparison. So the first part of this may look kind of, why are we talking about this? 0 is less than 1 and 1 is not less than 0. Can we buy that? Okay. Does anyone want to argue? No? Okay, not yet. Okay, maybe there will be some other things that you want to argue later. So these two are basically axiomatic, which means, yes, we can establish these as facts without any further proof. Okay? So now we move on to comparing x and y. I want to find out whether x is less than y. That's all I want to find out. I don't care about whether they're equal to or greater than. I just want to know whether x is less than y. Is that okay? Because we can translate other comparison operators to just less than. And then just like with our other types of notation, x underscript lower script subscript. Thank you. So x subscript x subscript x x subscript I. Okay. I really should be a politician. So x subscript I is bit I of x. Okay. And we start counting from 0, okay? Same thing with y. So this way, I have a way to designate a particular bit in a number. So we know that xi represents the quantity or whether the presence of 2 to the power of I because we are talking about base 2 numbers. Is that part okay? Is this part of the sentence okay? We know that xi represents the quantity in parentheses presence because it's either 0 or 1, so the quantity in this case is really the same thing as the presence or absence of 2 to the power of I. Is that part okay? Okay? Of the value represented by x as a bigger binary number. So that's basically, so now we have a question. Do we know whether 2 to the power of n is greater than the summation of I going from 0 to n minus 1 of the term 2 to the power of I? Can we know that for sure? So I'm really asking, for instance, let's say n is 3. Do we know that 8 is greater than 1 plus 2 plus 4? Now, after you carry out the calculations, you will say, yep, we know that. But do we know in general that is the case? And if we are not sure, can we prove it? Can we prove that 2 to the power of n is greater than the summation of I going from 0 to n minus 1, 2 to the power of I? Can we prove that? Yep, we can certainly prove that because that's right next to this claim here. So the way we prove this is a preview if you have not taken 440. This is a preview of the concept of proof by induction. If you have taken 440 already, this is a review of the concept proof by induction. So the way it works is we have to find a base case. So we have to find a base case. So we can say when n equals to 1, is that theorem true when n equals to 1? Tell me. I mean, you can substitute, right? 2 to the power of 1 is what? 2. And then on the sigma side, how many terms do we have? One term, which consists only of 2 to the power of 0, which is 1. So now the question is 2 greater than 1? We got that. That's our base case. In a proof by induction proof, once you have a base case, then you move on to the induction step. In the induction step, you start with what we call the induction assumption. The induction assumption looks kind of funny. It's like this, okay? We'll just pick a k, okay? It's not a very specific value. We just make an assumption that the theorem holds true for 2 to the power of k is greater than sigma I equals to 0 to k minus 1, 2 to the power of I. It's an assumption. But assuming that is true, can we move on to show that the next step up is also true? That's the trick of proof by induction. You can make an assumption, but you cannot jump. You can only use the assumption to prove the next case. You're stepping up just by one. So let's see. I mean, the proof is right here. So let me move the mouse pointer over just a little bit. But I can click here just so that we can focus on that particular proof here. So the question is, can we prove that 2 to the power of k plus 1 is greater than this part of the sigma? Well, one thing we can do for sure is we know 2 to the power of k plus 1 is 2 to the power of k plus 2 to the power of k. Can we buy that? Okay, this is good. But we also know one thing, is we know something about this. We know that 2 to the power of k is greater than this particular sigma here. So I break that. So I take out one term on this side. I take out this 2 to the power of k. But I have to take out 2 to the power of k on the other side as well. But the way I take it out is to remove one term from the sigma. Because if you look at this sigma here, the last term is when I equal to k. So I can take that out by changing the index, the range of the index, and back it up by 1. Is that okay? Now we have the proof, because this is already established as the induction assumption. So now I can go back to here and go like, yeah, we know this already. That was the assumption. And now we're done. We're done with the proof. Isn't that cool? If you have taken 440, you would say, nah, yeah, we know this already. Nothing exciting. But proof by induction is a very powerful proof in computer science specifically. Because in computer science, a lot of things are discrete, okay? Here's one, this is the next one, this is the next one, this is the next one. In calculus, things are continuous, so it doesn't benefit as much from proof by induction. But in computer science, because we go step by step in discrete steps, that's why it benefits more from proof by induction. So you don't have to understand proof by induction in this class, because this is not discrete. Yep, go ahead.
Yeah, the 2k plus 1 is the same thing as 2k plus 2k?
Yes, because 2 to the power of k plus 1 is 2 times 2 to the power of k, which is the same thing as 2 to the power of k plus 2 to the power of k. So that's how I derived, the left-hand side. So are we? Yes.
So I thought it's like 2 to the power of k times 2 to the power of 1 plus 2 to the power of 1. It only works if it's 2.
Okay, I think I skipped one step. That's why. Okay. I'm pretty sure my little stylus is working today because I was using it earlier. Okay, so let me show you the proof here. This class is not really about proofs, but I still want to answer those questions because I think it is important to utilize mathematics and proofs whenever it is possible. Okay, so we got 2 to the power of k plus 1, and it is equal to 2 to the power of k times 2 to the power of 1, right? What is 2 to the power of 1? 2, right? So we have 2 times 2 to the power of k, which I can then rewrite as 2 to the power of k plus itself. Is that okay? Yes? No? It's good? Okay. Now this is algebra, okay? This is algebra, okay, I wouldn't say that. So this is algebra, I would say about 10th, 11th grade algebra. So if this is bothering anyone, it's time to review this type of mathematics. I'm not kidding. I'm dead serious. Okay, because because future classes will be very difficult without a basis, a foundation like this. Okay. So are we good with that proof? Because I just want to clarify the derivation on the left-hand side. So this is okay? All right? Okay. So what this has done so far is really just proving this particular theorem. It is always true that 2 to the power of n is greater than the sigma notation where I goes from 0 to n minus 1, and each term is 2 to the power of I. We have just proven that this is always true. So you might look at this and go like, why is that useful? Well, the usefulness of this theorem will be obvious later on. So now we want to say, okay, do you guys have any questions? Any questions? Nope? Okay. Because I was thinking you guys had a question because you were kind of talking. All right, so now we look at x and y, and we say they have m bits. Okay, so we're looking at two numbers, x and y, and both are binary numbers, and both have m explicit digits. And we'll assume that xi equals to yi equals to 0 for all the i's greater than or equal to m, because they are out of the representation of the numbers. The numbers only have m digits, which means the explicitly represented digits go from x0 to xm minus 1. So xm is actually out of the range. So anything that's out of this range can be assumed 0. We're talking about unsigned representation here. Are we doing okay so far? Okay. And then the next notation, I don't think is actually needed, so we'll forget about this notation because it's actually not needed, which is used only to refer to a range of bits. I don't think we'll need that, so we can ignore that. So here's the thing. You can make an assumption, okay? You can assume xi equals to yi for some p, and I is greater than p. Why can we make this assumption? Because, well, if p is m minus 1, we can certainly make that assumption because those are all zeros. Is that making any sense? All right? Okay, so let's look at the next line then. So based on the assumption that every bit, beyond bit p are the same, let's look at the first case here. If xp equals to 0 and yp equals to 1, then we know x is less than y is true. Can we claim that? Regardless of all the less significant bits. Is that okay? Because the only time you can say, I don't buy this, is you can say, well, what if all the less significant bits of x are all ones and then all the less significant bits of y are all zeros? Is this less than still going to hold? Well, based on the theorem that we have just proven, yep, x would still be less than y, or the value represented by x would still be less than the value represented by y. This is the reason why I have to establish that particular theorem first. Is that okay? Yes? Do you guys see the connection between the theorem and what I'm claiming here? Okay. So now we move on to the next case where xp is 1, yp is 0. Then we know x is less than y is definitely false. I can stop right here. I don't even need to look any further because of the same theorem. Is that okay? So the only thing left to do is, what if they're the same? Well, if they're the same, we move p down by 1. Because that assumption is basically saying, okay, we know all the bits are the same for up to bit p, so that means we don't have to be concerned about that. What if p equals to 0? In other words, we found that all the bits are the same between x and y. Well, then x is less than y is false because the two numbers are the same. Is that okay? Is that making any sense? All right. What does this have anything to do with what we have done already? So let's check this out. This is only expressed by the individual bits, and this is what I want to claim. So the claim, I use the notation v of x to represent the value represented by x. X is a number, is a binary number, and v of x is the value represented by the bit pattern x. And we want to interpret it unsigned, okay? So this is what I want to claim. I will claim that Vx, the value represented by the binary number x, is less than the value represented by y as a bit pattern, if and only if Tm, the borrowed bit from column m, equals to 1. Now that's a pretty big claim. It's like, oh, we can just look at the borrowed bit, m, and then we can tell whether x is less than y or not. So it makes sense, but can we prove that? So the rest of this is really just a proof. This is an equation. I certainly hope that you already know what this means. The b is a function. So when you subtract fyi from xi, single bit subtraction, do we end up with a borrow? That's what the b function is. Okay, kind of like the carry function, except this is for subtraction. And this is the b function to subtract ti, which is the borrowed bit of bit I, from qi, which is the intermediate subtraction result of bit I. And this is the borrow of that. Okay, so once again, these notations or the meaning of these letters, x, y, q, t, and that should be fairly familiar by now. Okay, because we talked about those in the previous class. This is not new. Okay, when we talked about binary subtraction, we already presented this equation. Okay, so it's not new at all. So now we want to fit that into what we just did. Okay. And once again, we make the same assumption here. We're basically saying for every I that is greater than p, bit I and bit y, the bit I of x and bit I of y are the same. And we also claim that all those carry or borrow bits are identical as well. Okay? And then we move on to the next one. So we are looking at the first bit that are different. Now, is this saying bit TP is true or false? It doesn't say a single thing. It just says that they are exactly the same. So now we encounter our first case. Okay, this is the first case where the bits are different. Okay, bit P of x and bit P of y are different. How are they different? XP is a 0, YP is a 1. We talked about this before. But this time the question is, what is going to be the borrowed bit as a result of this, of p plus 1? So we plug this in, okay? So because we look at this equation, right? So xp is a 0, it goes into here. Yp is a 1, it goes into here. We don't really know this one, but we kind of know that this has to be a 1. So the question is the result a 1 or not? If you look up at the truth table of the borrow bit computation, if you subtract a 1 from a 0, you do end up with a borrow. And because this is an OR operation, that means we guarantee t subscript p plus 1 is a 1. Is that okay? But once we know that t subscript p plus 1 is a 1, we can now backfill t of I for I is greater than p plus 1 to be all 1s. And do you know why that is the case? Okay, so it's probably better if I use a concrete example. As concrete as I can get it. Okay. So we have bit p here, bit p plus 1, p plus 2, blah, 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 all the way up to m minus 1. Okay? And we claim that all the bits are the same, from p plus 1 to m minus 1. They are all the same. Okay? So here's x and here's y. So we are basically saying, this bit equals to this bit here, Okay, I shouldn't use, it's not a 0, okay? We don't know what it is, but we know they are the same. This bit equals to this bit equals to this bit still equals to this bit here. But this is a 0 and this is a 1. This is the most significant bit that are different between x and y. That's basically what I'm saying. Is that okay? So when you look at the long subtraction format, oops, okay, we know 0 minus 1 is a 1, right? So I keep touching the other window. So we know this is a 1. We kind of don't know what this is, but we also know this is a 1, don't we? Because this is the borrow of 0 minus 1 over here. Is that okay? But we also know this is a 0 because these two bits are the same. Okay, let me use the mouse pointer. We know this bit and this bit are the same, so we know this location has to be a 0. Does that make any sense? So that 0 minus 1 will result in a 1 over here. And then we have all zeros here, and then we have all 1s over here. So that means at the very end, we still end up with a borrow here. And that would be the borrow bit Tm as our last borrow bit of the entire calculation. Yep?
So it means y greater than x.
This means x is less than y. That is correct. Yep. Yep. Mm-hmm. So we can conclusively know that x is less than y if and only if the overall borrow bit is a 1. Is that okay? All right. So back to the notes. What if xp is a 1 and yp is a 0? Can we conclusively say that x is less than y is false? That's the next question. So let's check it out. So we look back to this example here, and I'm going to change the example just a little bit to meet this requirement. Okay? So this is a 1, this is a 0, and we kind of have to erase all of these bits here. Okay, so get rid of all of these, cleaned it up, there we go. And then we say this is a 1, this is a 0. This is the case that we're looking at. What is 1 minus 0? It's a 1, okay. Does it matter what borrow bit we have here? If this borrow bit is a 0, 1 minus 0 is a 1 without a borrow. If this bit here is a 1, we have 1 minus 1, which is a 0, which also does not result in a borrow. In other words, I don't care what this is, okay? I can put an X here to say that I don't know what it is. We still know that we end up with a borrow of 0 from the next column. Is that okay? What is the significance of this? Well, we can use the same argument for every other bit to the left. Because now we look at this bit minus this bit, which is guaranteed a 0. 0 minus 0 is a 0 with no overall borrow. This bit is the same as this bit, so the result is a 0. 0 minus 0 does not result in a borrow. So we can use this argument to backpropagate all the way to this and then end up with an overall borrow of a 0. In other words, if the most significant bit that is different between x and y is such that x has a 1 and y has a 0, you can conclusively, state that x is less than y is false. But you can also be guaranteed that the overall borrow is a 0. So I'm trying to correlate the borrow bit to the result of the comparison. Is x less than y? Well, so far so good. So now we get back to the notes here. The last case is really say, well, what if we work all the way down to bit 0 and none of the bits are different? Well, then for each column, you would not end up with a borrow. So the overall borrow will still be a 0. But when x and y are the same, x is less than y is also false. So once again, the borrow flag is reflecting the result of whether x is less than y. Is that okay? All right. So let's just say that somebody look at all this math here and go like, I have no idea what just happened in the past 10 minutes. Okay? If there's only one thing to take away from this messy math stuff, okay, what do you think it is? When you're talking about an unsigned interpretation of a binary bit pattern, after a subtraction, x is less than y if and only if the overall borrow is a 1. That's your takeaway. Are we good so far? Okay. What about the signed interpretation then? What if I look at the bit pattern and say, oh wait, I think this is going to be a signed representation. I think we are actually missing something in the signed representation thing, but we'll go back and fill that in a little bit later. So the first thing we want to do is to find out, for signed representation, how do we figure out the value represented by a binary bit pattern? So we want to figure that out. So what we want to do is, this is the same notation. M is denoting how many bits we are allocating to the numbers. So x subscript m minus 1 is what we call the most significant bit. It's the bit all the way to the left-hand side. It is also known as the sign bit, because if that bit is a 1, the value represented is negative. Otherwise, it is positive. Okay? I think this is where I need to stop, because I think I forgot to talk about the signed representation. We started to talk about signed representation, but we did not finish the entire thing. So we'll stop the comparison discussion at this point, and then we'll switch back to the previous note of signed representation, because we kind of need that to get to this part. Because I think, signed value representation, that's it. Okay. We started on this one, we just haven't finished it. Because this is where we started to talk about the number circle. And we also talked about the properties of negation. Remember this part here? But we did not get back to talk about how do we represent negative values. So we'll resume that discussion, and then we'll get back to comparison. Okay? So I think it would be helpful to kind of look at the number circle again. So here's the number circle. How many bits do we want to deal with this time? 3 or 4? Last time we used 4 bits. 3 bits? Okay. So this is 3 bits because we have 8 slots here. So it's 3 bits. So the first thing I want to do is to give each slot the binary representation. So we got 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Do we have any questions about this part? No questions? Okay. Now, one thing I do want to mention is this wheel, or the way I arrange the bits, has to do with the adder. Okay. If you add 1 to 0, 0, 0, if you add 0, 0, 0, and 0, 0, 1, what do you get? 0, 0, 1. What if you add 0, 0, 1 to 0, 0, 1? You get 0, 1, 0. If you add 0, 0, 1 to 0, 1, 0, you get 0, 1, 1, and so on. So I do want to point that out. Is if you use a 3-bit adder, and every single time you're adding 0, 0, 1 to the previous number, you can basically go through all the slots in a clockwise fashion. Is that okay? Can everybody kind of see that, kind of visually see that? Okay, good. So then the next question is, what about the value they're representing? Remember, a bit pattern has no inherent value being represented. It's just like sand, right? You go to a beach, okay, and you look down and you look like, That looks like a certain deity. No, no, it doesn't look like a certain deity to me. It looks like a car, okay? Or it looks like tax note to me. No, it looks like my grade. Because sand has no inherent interpretation. It is you interpreting the shape and the arrangement of the sand, and you are giving it meanings. Value is meaning. Bits is raw. It's just, well, this is a bunch of sand, just so happen to arrange this way. It has no inherent meaning. So these zeros and ones have no inherent meanings. It really is just saying, oh, we got 2 1s and then a 0 arranged in that particular fashion. What is it representing? We don't know, and we don't care. It can potentially mean, on the screen we have 1 pixel that is lit, 1 pixel that is lit, and 1 pixel that is not lit. It can be that. It can be a traffic light, right? This is the red light, this is the amber light, and this is the green light. It can be the traffic light configuration. We don't know what it is representing. Is that okay? So I'm going to use blue to say, well, what if I choose to interpret the bit pattern as an unsigned number? Then what would be the value represented by each of these bit patterns? So that's what the blue is going to be. So the blue is going to say, okay, we can just do this. Is that okay? And I'm going to use another color. I'm just going to pick one. Green. Okay, we can use green. So the green one is saying, but I want to interpret all of these bits as a representation of a signed value. Okay? So in that case, I will still say 0, 0, 0 is the same thing as the value 0. 0, 0, 1 is still the value of 1, 2, 3. And then I go like, wait. I have just used up 4 out of 8 slots for non-negative values. Okay? 0 is non-negative. So I have used up 1/2 of the bit patterns available to represent non-negative values already. I probably want to use the other ones for negative values. Does that make sense? Sort of logical, right? So where should I put -1 then? Well, I got a few choices. I can put -1 here, or I can put -1 over here. Doesn't make sense to put -1 like in the middle of something, right? So which one should I choose? Then you ask the question, if I add 1 to -1, what should I get? 0, okay. So if I remember, adding 1 is moving in a clockwise fashion. So if I move clockwise, I end up here. That means -1 really should be here. Is that making sense? Yes?
Yeah. What were the blue numbers?
The blue numbers are representing signed interpretation of the bits. And then the green numbers are representing, I take it back, sorry. The blue numbers represent unsigned interpretation, and then the green is the signed interpretation. So I will put -1, -2, -3, and -4 over here. Are we good so far? So it's all good? Okay. Now we look at this and go like, I can see -1 and 1. I can see -2 and 2. I can see -3 and 3. So now the question is there a way for me to do negation, arithmetic negation? So that I can say the negation of 3 is -3, the negation of -3 is 3 itself. Is that okay? So we'll work on that. But if you look at the green versus the blue values for the negative side, okay, just focus on this side here. Do you see a pattern? You look at -1 and 7, you look at -2 and 6, you look at -3 and 5, and you look at -4 and 4. Do you see a pattern? If you add up the absolute values, they are 8, okay? But you don't even have to look at absolute value. You just say, if I subtract the green from the blue, I get 8. Is that making any sense? Because 7 minus negative 1 is 8. 6 minus negative 2 is 8. 5 minus negative 3 is 8. 4 minus negative 4 is also 8. Is that okay? So that means if I want to do arithmetic negation, I actually have a pretty quick way to do it. Because what I do is I can, okay, so let me present the equation first. Okay, so I'm going to switch back to black ink here. Okay. So we notice that 7 minus negative 1 is 8. We notice that 6 minus negative 2 is also 8. And so on, down to 4 minus negative 4 is also 8. So we make that observation. And we go like, how can we make use of this observation? So now let me ask you a question. I know 3 is supposed to look like this, okay? How can I find out how negative 3 is going to be represented? That is the question. Yep. Subtract the 3 from 8. Very good. Oh. Okay. So your answer is correct, but let me repeat that, okay? So in order to find out what is the representation of negative 3, all we have to do is to subtract 3 from 8 and then find out what that representation looks like. All right? So can I make this more formal? So make a new page after. Okay. So let me just write this to find the representation of a particular value x, okay? All we have to do for a 3-bit number is to say, what is 8 minus x, okay? So it is the representation of negative x for 3-bit numbers. That doesn't seem hard. We only got one problem. 8 cannot be represented using only 3 bits. Because we know how to do binary subtraction, don't we? We can do this. X is a 3-bit number. We know how to do a 3-bit by 3-bit binary subtractor. Not a problem. The problem is 8 is not represented cannot be represented using only 3 bits. Because it's 1 followed by 3 zeros. So, well, it seems like we have a problem here. What if I do this? Can you buy that? Yeah. 8 is 1 plus 7, right? Can I now do this first? Okay, that is cool. I look at this and go like, but wait, that is a funny subtraction. Because what is 7 as a binary number? It's 1, 1, 1. It is 1 plus 2 plus 4. Is that okay? And if you have a number like that and you subtract another number from it, the result is very interesting. Okay, so let me show you what it looks like. Okay, so we'll use 3 as an example. So we have 1, 1, 1, which is 7, minus 3, which is 0, 1, 1. Do we end up with a borrow of 1 anywhere in this subtraction? We don't, because every single bit of x is a 1. And from the borrow bit subtraction equation, we know that if you subtract anything from 1, the borrow bit is going to be a 0. We don't have a borrow. But we have something that's even more interesting. Because the result, the difference, 1 minus 1 is a 0, 1 minus 1 is a 0, 1 minus 0 is a 1. So now if you compare this number and this number, do you notice anything? They're negations of each other, bitwise. Does that make sense? Because not 1 is 0, not 1 is 0, not 0 is a 1. Are we good so far with this observation? Okay. So that means our calculation can now be done by 1 plus tilde x. Now tilde x is the bitwise not operator in C and C++. It means exactly the same thing as taking 0, 1, 1 and turning it into 1, 0, 0 as a 3-bit number. Is that okay? It's bitwise not. But this also has a different name, a longer name. It's called 1's complement. So this whole thing is basically 1 plus, I call it C1 of x, and I'll explain what is C1. This is called 1's complement. Okay. What about the whole thing? 1 plus 1's complement of something. That whole thing is called, guess what? 2's complement. So this entire thing is called 2's complement of x. And it does the same job as arithmetic negation. So in normal math, in all of your other classes, you use this notation, but in assembly language programming and computer architecture, we boil it down to 1 plus the 1 plus the 1's complement of x. Do we know how to do this operation in logic gates? Well, okay, let's focus on one thing at a time. Do we know how to do 1's complement, which boils down to negation, right? Negation can be done by NAND gates. We got that? What about the plus here? This is a binary addition. Do we know how to do binary addition? Yes. So this whole thing can be done using transistors. And I claim that this is the same thing as the negation of x. Okay? So in this class, I use C2 of x as a notation to represent it is representing 2's complement of x. Okay, so some of you may say, oh, I'm not really so sure about this. Well, the first thing you can do is to check it out. Apply 2's complement to some 3-bit numbers and see whether it works out or not. Does it make sense? Yes? Okay. So we'll try this out on a few values, okay? Not just one, but a few. So the first thing we'll say is, well, let's do this. We want to find out what is the 3-bit representation of -3. What -3? You put a 3 here, how come it is representing -3? Remember, C2, 2's complement, is the same thing as arithmetic negation. So this really should be the same as -3. But one is the value, the other one is the bit representation. Okay? This side is the value, this side is the bit representation. All right, so let's do it. C2 of 0, 1, 1 in base 2, because I have to convert it into binary first, is the same thing as C1 of 0, 1, 1 in base 2 plus 1, which is the same thing as negating all the individual bits. Can someone tell me what it is? 0, 1, 1, you flip all the bits, it becomes 1, 0, 0. Okay, 1, 0, 0 in base 2 plus 1, which is 1, 0, 1 in base 2. Does that match the number circle that we drew earlier? It does. Okay. So here's the trick. If I apply 2's complement to 1, 0, 1, I should get 3 back, don't you think? That's one of the properties of arithmetic negation. If you apply that twice, you get the same value back. So let's try that. So now we say, what about the 2's complement of 1, 0, 1 in base 2? So, well, same thing, right? 1's complement, 1, 0, 1 in base 2 plus 1. And what is the 1's complement of 1, 0, 1 in base 2? 0, 1, 0. Okay. So we got 0, 1, 0 in base 2 plus 1. And guess what we get? We got 0, 1, 1 back, which represents 3. So when you look at the representation of -3, you apply 2's complement to it, you get the representation of 3 back. Seems to work. I bet this doesn't work on 0. Right? What is the negation of 0? It should be 0, right? Okay, well, let's give it a try. I think I need a new page. So now we say, what is the 2's complement of 0, 0, 0? Okay? It is the 1's complement of 0, 0, 0 in base 2 plus 1, which is 1, 1, 1 in base 2 plus 1. And then some of you are going to say, ha, gotcha. Nope, you did not get me. It just has an overall carry of 1, but the result is 0, 0, 0. So I'm still right. It does work out. Pretty cool. Right? But one thing we still have to kind of go back and look at is, if you look at the number circle, if I ask you just one thing, if I just need to know in signed representation whether the value is negative or not, that's all I ask, okay? I don't care about how negative. I just want to know whether it is negative. What do you look at? Which simplest thing do you use to determine whether a representation is the representation of something that's negative or not? The most significant bit. Very exactly, okay? That's good. So if you look at the most significant bit, which is the leftmost bit, okay? If it is a 1, it is a negative value. If it is a 0, it is a non-negative value. Don't say positive, because 0 is not positive, okay? So are we good so far? So that's why it is called the sign bit. The most significant bit is called the sign bit, because it alone can tell you the sign of the value represented. Is that okay? Yes?
So to get -5, we need to go 4 bits.
That is correct. There's no -5 when you only have 3 bits. That is a very good observation, because it will come in handy later on, okay? So are we good so far? Okay. But then I have another question. I look at this and go like, but can we come up with a sigma notation so that we can figure out what is the value represented, the signed value represented by a bit pattern? What is that going to look like? Okay, what do you guys think? Well, we know a part of it is pretty easy, okay? This part, the non-negative side, is super easy, right? Because it's the same as an unsigned value. Each bit is only representing the presence or the absence of a power of 2. We got that, okay? But the negative values is kind of like, it's kind of throwing a wrench into this whole thing. Or maybe not, too bad, okay? So when you look at 1, 0, 0, which is representing -4, how are you going to work that out? How do you interpret this 1 here? So as it turns out, that is where you say everything other than the most significant bit, we process it just like usual. But the most significant bit, we arithmetic negate it first. So this most significant one is representing the presence or the absence of, guess what? -4. Now see if that works for all of the other numbers. So we'll pick 1, 1, 0, okay? So ignoring the most significant bit, we have 1, 0, which normally represents just 2, right? The most significant bit 1 is representing the presence or the absence of -4. So this is 2 with the presence of -4. 2 minus 4 is -2. It does work. So now the question is, well, does it work in all cases? This is a 3-bit number. Does it work with a 64-bit number? What do you think? It does. So with that in mind, I'm going to switch back to my notes here. And I have to find that module that we were looking at. earlier, and I think it's here. All right, that's it. Okay. So this is back to the comparison slide. So this is saying, what is the value represented by x? But I want the signed interpretation this time, okay? And the way we do it is we ask, well, what is the most significant bit? X subscript m minus 1 is the most significant bit, otherwise known as the sign bit, okay? So we say if the sign bit is a 1, then it is this equation, otherwise it is that equation. But through all the calculations, we can just boil everything down to here. So what is the last one here? The last form of the sigma notation. It's saying the same thing that I just said earlier. The sigma notation does not end with m minus 2 anymore. It only ends at m minus 2, which means the most significant bit is left out of the sigma notation. I'm summing up all the powers of 2 based on all the bits except for the most significant bit. Add them all up, okay? And then I subtract x subscript m minus 1, which is the sign bit, times 2 to the power of m minus 1, which is actually the correct power of 2 at that position, but I am not adding it, I'm subtracting it. That is how we come up with the value, the signed value, represented by a bunch of zeros and ones. Is that okay? Does it match what we observed on the number circle? It should, okay? I'm trying to make sure that you guys are making connections between the picture and the equations. You can ignore the derivation if you want to, okay? So you can ignore all of this derivation, but the bottom line is v of x equals to this equation here, this formula here. So are we good so far with this part? So the cricket, the cricket is back. Okay. So now we look at x is less than y, if and only if x minus y is less than y minus y, if and only if x minus y is less than 0. Can we buy that? I mean, that seems to make sense, right? Just from algebra, that seems to make sense. Okay, so if x is less than y is true, if and only if the difference between x and y is less than 0, then we can just look at the sign bit after a subtraction and call it a day, in theory. Is that making any sense? Yep. Yes, this time I actually remember what I said. Can we follow this derivation? X is less than y if and only if x minus y is less than 0. Normal algebra. We are not talking about binary stuff. We're just talking about normal algebra. Is that okay? But we are looking at something being less than 0. Something less than 0 means something is negative. If something is negative, what do we know about the sign bit? If something is less than 0, the sign bit is a 1. So that, it seems like, is a very easy answer. We do the subtraction. We look at the sign bit of the difference. If it is a 1, then x is less than y. Done. Seems pretty easy, right? So we'll put it to a test, right? We'll test it out and see whether it works or not. Okay, so we'll test that, and we'll pick some values from the number wheel from before. We'll pick 1 and 2. Okay, so we'll say, is 1 less than 2? Okay, in other words, we are asking, is 1 minus 2 less than 0? Okay, I know it is obvious, okay, but we'll double check. But we want to do this in binary subtraction because we want to know whether the sign bit is a 1 or a 0. Okay, so we have 0, 0, 1 representing 1, 0, 1, 0 representing 2. Do the usual long subtraction thing. 1 minus 0 is a 1. 1 minus 0 is a 1. Neither subtraction gives me a borrow. 0 minus 1 is a 1, and that immediately gives me a borrow. 1 minus 0 is a 1. 0 minus 0 is a 0. 0 minus 1 is a 1 with an overall borrow. I don't care about that overall borrow. Remember, I only want to look at the sign bit of the difference, which is this guy here, and it's a 1. That tells me that x is less than y, or the signed value represented by x is less than the signed value of y. That works, okay. But then you can say, well, these are non-negative numbers. I bet this doesn't work with negative values. So we'll check it out with negative values as well. Okay, so we'll say is, oops, okay, keep touching somewhere else. Okay, so before we do that, I'm gonna make sure I cannot touch the other part of the screen. Okay, so this time we'll say is negative 2 less than negative 1? It should be the case, right? So now we want to say negative 2 minus negative 1, is that less than 0? And you guys say yes. But is that the result in a binary subtraction? That's what we want to know. How do we represent negative 2? Do you guys remember? Okay, look up your number wheel. 110, thank you. 110 is representing negative 2. 111 is representing negative 1. We do the binary subtraction here. 0 minus 1 is 1 with a borrow. 1 minus 0 is a 1. 1 minus 1 is a 0. 0 minus 1 is a 1 with a borrow. 1 minus 1 is a 0. 0 minus 1 is a 1 with an overall borrow. The sign bit of the difference is a 1. So in fact, negative 2 is less than negative 1. It works out. Now, this is the problem of spot checking using test cases, because someone might be sufficiently convinced and say that, yes, we can rely on just the sign bit because it works in both of these test cases. And then I suggest the third test case. So the third test case goes like this. Okay? And this time I'm comparing negative 2 on this side and 2 on the other side. Okay? I'm asking, is negative 2 less than 2? And you guys go like, this is even easier than the previous ones. Okay? Why do we even bother with this? Because it doesn't work. Okay? And you cannot, and then you say, how can this possibly not work? Actually, does this one work? This still works. Make that 3. Then you guys go like, that's crazy. I mean, 3 is even more than 2. How can this not work when the other one works? Well, we'll check it out. So that is basically asking, if I look at negative 2 minus 3, is that less than 0? That's the question. And you look at this and go like, negative 5 obviously is negative. Well, but we have to do this in binary, okay? So the key is what seems to make sense to you in base 10 may not work equally well when you're doing everything in binary, in a fixed width format. Okay, so that is the key. Okay, so you guys already looked up. Negative 2 is 110. I know 3 is 011, so we just do the subtraction, okay? No big deal. Okay. 0 minus 1 is a 1 with a borrow. 1 minus 0 is a 1. 1 minus 1 is a 0. 0 minus 1 is a 1 with a borrow. 1 minus 0 is a 1. 1 minus 1 is a 0. There's no overall borrow. I don't even care about the borrow. I look at this overall, the sign bit of the difference. This tells me that negative 2 is not less than 3 because the sign bit of the difference is a 0, not a 1. Oops, that didn't work. So the sign bit alone cannot tell you whether x is less than y. Obviously, it's not working in this case. Is that making any sense? So the question is, okay, so there are 2 points, okay, 2 main points to make here. The first one is, okay, it is not working, but the second point is more important. Why is it not working? Yes, because -5 is out of the range of the values that can be represented when you only have 3 bits. Because in the number circle, what is the value taking the place that you would otherwise put a -5? A 3. And 3 is a positive number. Okay? That is the reason, because we cross that border, we cross over that line, and that's why it's not working. It's called an overflow. We are overflowing what the 3-bit number can represent. Is that okay? Okay. Well, are there other ways to overflow? Well, the answer is yes. So let me show you another way that we can overflow. Oh, I actually put this in the wrong page. Okay, so the other way that you can overflow is something like this. Is 3 less than -2? Okay, you go like, no. Well, but if you use the sign bit of the difference after a binary subtraction to determine, then it would actually say yes. You go like, what? Well, let's check it out. So this is really asking 3 minus -2, is that less than 0? Then you go like, no, because it is 5. 5 is not less than 0. But remember, you're doing everything in base 10 and not in base 2 with only 3 bits. So now we have to carry that calculation using only 3 bits binary operation. Okay? 3 is 0, 1, 1. -2 is 1, 1, 0. Okay? So we carry out the subtraction. 1 minus 0 is a 1. 1 minus 0 is a 1. Neither contributes a borrow of 1. 1 minus 1 is a 0. 0 minus 0 is a 0. Neither contributes a borrow of 1. 0 minus 1 is a 1 with a borrow. 1 minus 0 is a 1. So if you only rely on the sign bit of the difference, this would tell you that 3 is, in fact, less than -2. But it's not the case. Why is this not working? We know it's not working, but why is it not working? Because 5 is not on the number wheel either. But then someone's going to say, but 5 was on the number wheel. It was blue, which means only if you're using the unsigned interpretation, you can have a representation of 5. But if you look at the green values, 5 is not on the wheel. You cannot represent the value of 5 using only 3 bits. Once again, we have overflown the values that can be represented. Is that okay? Yep.
What should we do in this?
So what we should do now is to say, well, we know the sign bit cannot be trusted when there's overflow, right? In fact, we know it cannot be, we reliably know that the sign bit cannot be trusted when there's overflow. So if we can also determine whether there's an overflow, then we are good. Combining the sign and the overflow, we should be able to know the answer. Okay? We got 3 minutes. I think we got enough time to do this. Because you guys know this stuff already. Okay, so we have 4 situations. We have, I keep touching the other screen. Okay, negative value minus positive value. Negative value minus negative value, positive value minus negative value, and then we have positive value minus positive value. Okay. I only need to know what sign does not make sense. Okay. When you have a positive value minus a positive value, what is the result? What is the sign of the result? Well, it can be positive or negative, right? So the sign bit can be either way. So in this case, it can be positive or negative, the difference. Is that making any sense? Okay. The same thing applies over here, right? Because if you subtract a negative value from a negative value, well, it can go either way, depending on the magnitude. But the other two has a definite, sign of the result. If you subtract a positive value from a negative value, the result should always be negative. If you subtract a negative value from a positive value, the result should always be positive. Is that okay? So what if I get a positive value when I subtract a positive value from a negative value. Instead of getting what we expect, we're getting the other sign. What is that telling you? Overflow, okay? So let me move this up a little bit. So negative value minus positive value ending up with a positive value, overflow. What about the other one? This one over here. Positive value minus negative value ending up with a negative value. Once again, we have overflow. This is how we can determine after a subtraction whether we have an overflow situation or not. Okay? Darn it, we are out of time. So we can continue this on Thursday. You won't need this, for your lab, so don't worry. We are on track in terms of lecture. I'll see most of you at the lab in 10 minutes. Yes?
Convert, you say that minus 2 isn't it minus 2, yeah, it's like 1, 1. If we flip it back into 0, 0, 0, just there.
Because you have to add 1 to it. 2's complement is 1's complement plus 1. So if you add 1 to 1, 1, 1, you get 0, 0, 0. Because the sum can only have the same number of bits as x and y.